In the previous lectures, we have seen about what is enthalpy, the units of enthalpy, what are the types of enthalpy and how to calculate enthalpy numerically. Here we are going to look at the potential energy diagram relating to enthalpy. This is extremely important because it helps you in deciding whether a given reaction pictorially is exothermic or endothermic. Just an explanation of what is exo and endo, just to make sure everybody knows. Exothermic reactions are where the reaction liberates heat out of the system, so my reactants are higher in energy than products. Endothermic reactions want heat, so they absorb the heat and my products are higher in energy than my reactants. Okay. Here I have chosen the exothermic potential energy diagram. A mirror image of that would be the endothermic. You can draw it yourself. Okay. This is different. This is catalyzed reaction. This is uncatalyzed reaction. So when you take an exothermic reaction, my reactant goes to products. It wants to give out energy. But just like that, it cannot give out energy. If it can happen, then all the reactions in nature would be completely done, the exothermic reactions. But what we have is, the reaction is exothermic, but still nevertheless, it has to cross a barrier just like a mountain. You have to go on top of a mountain to go into a plateau that is lower in level. Okay. Alright. So now let's say this is the height of the mountain. So the total energy that you need to have, it's just like a Neet cutoff. How much marks you need to get into the dream college, government college, let's say MMC or whatever it may be. Okay, that's the cutoff. But you are not at zero today, you already have some amount of preparation. So what is the excess preparation you have to take? Okay, the total cutoff that you need to get, that's called threshold energy. So anybody who crosses the threshold energy will go to the product side, okay, top of the mountain. But you already have some amount of energy, that is your internal energy that you already have. Okay, the internal energy of product is lower than the reactant, so hence it is exothermic reaction. Okay, the amount of energy that you need to gain on top of your internal energy to meet the threshold energy is called activation energy. Okay, and for forward reaction I have to go from here till here, so this is the difference in energy I have to gain. This is called E activation, and I am going to say forward. When I look at the reverse reaction, this is the amount of energy I start with. The mountain is the same height, I have to climb so much, so this is the E activation energy reverse. For exothermic reaction, so what all can we say is, if it's an exothermic reaction, E activation forward is less than E activation reverse. So whatever I write like this is going to be opposite for the endothermic reaction. Okay. So the next thing what we can do is, okay, when I look at it, my reactant energy is this, product energy is this. What is the difference between them? The difference between them should be the delta H of reaction. Delta H of reaction is delta H products minus delta H reactants. Okay. So this is absolute thermodynamic. It does not decide what path you take. Okay. Path is the kinetic side. This is the thermodynamic side. So you can go even higher, even lower, doesn't matter. This is not going to change. That's a delta H. So now I have my delta H equals delta H product minus delta H reactant. In this case, product minus reactant is negative. It's exothermic reaction. Coincidentally, that is also true. I can get this by doing E activation forward minus E activation reverse. E activation forward minus E activation reverse. So if I know this, I can actually equate these two equations, 1, 2, 3, 4 quantities, 3 of them are known, 1 could be the unknown. Okay. So now again we have established that it's an exothermic reaction. This is the E activation forward, this is reverse. Forward is always smaller than reverse for an exothermic reaction. Okay. Now this is very simple. Now going into a particular reaction, that mountain may be very, very high. I don't want to climb that much. I want to decrease it. What can you do? You can raise the temperature, okay, to go to the top. You can temperature raise panningana, internal energy of reactant goes up, product goes up, my delta H is still the same. But temperature raise panna, enak inda amount kammi agum. So I can actually get the reaction done faster if I increase the temperature. Hence many reactions in chemistry, particularly organic, you see at elevated temperature. Okay, but what happens is, just that is not enough, because sometimes temperature neenga heat pandringa, and the reaction heat pandringa appadina side reactions nadakum, elimination reaction are possible where I want substitution. That's one thing. My second problem is, my product or reactant might not be stable at that temperature. So instead of that, what I do, I try to use a catalyst. What a catalyst does is, I don't agree with the way that Neet gives credit for this. Some of the books also say catalyst decreases the activation energy. This is the potential energy diagram for a catalyst. The black color is uncatalyzed reaction, the blue color is catalyzed reaction. If you see, my E activation forward has decreased, forward catalyzed, and also by a similar magnitude E activation reverse has decreased for catalyzed. Okay. Now if you look at the diagram carefully, both the forward and reverse are decrease in activation energy, but the common thing what a catalyst does, common answers that is given in most books is your activation energy is decreased for a given reaction. That's not true, that's not the right way of saying it. Okay, imagine that you are going to a mountain and I don't want to go on top of the mountain. What I do, I drill a hole and I put a tunnel. இப்போ டனல் இருக்குன்னா நம்ம மேலே வேகமாக போவோம்னா கீழ் வழியாக போயிடலாம். ஸோ நம்ம சீக்கிரமாகவும் போய் சேர்ந்துட போகிறோம் ஏன்னா பார்த்து கிட்ட. ஸோ மை கேட்டலிஸ்ட் மேக்ஸ் த ரியாக்ஷன் கோ ஃபாஸ்டர். ஓகே, பட் இட் ஆல்சோ மேக்ஸ் த ரிவர்ஸ் ரியாக்ஷன் ஃபாஸ்டர். இட்ஸ் நாட் அ ஒன் வே டனல், இட்ஸ் அ டூ வே டனல். ஸோ நீங்கள் வேகமாக A to B போகிறீங்கன்னா சீக்கிரமாக B to Aவும் வருவீங்க. ஸோ த கேட்டலிஸ்ட் அஃபெக்ட்ஸ் போத் ஃபார்வர்ட் அண்ட் ரிவர்ஸ் ரியாக்ஷன் ஈக்குவலி. It affects the kinetics of the equation. சீக்கிரம் போய் சேரலாம், ஆனால் போய் சேர போகிற இடம் ஒன்று தான். ஸோ மை டெல்டா H is same in both cases. So this minus this is same as this minus this. So my delta H does not change for a catalyzed or uncatalyzed reaction. Okay, but the right way of saying my top of the mountain has not changed. So the catalyst has not really decreased your activation energy. The right way of saying it is what a catalyst does is it has found an alternate pathway with less activation energy. வேற ஒரு டனல் வழியாக போகிறீங்கன்னா அப்போ அவ்வளோ நீங்கள் கிளைம் பண்ண வேணாம். ஸோ இட் ஹஸ் ஃபவுண்ட் alternate pathway, another path where the activation energy is less. Okay, that's the right way. If that option is not there, then in Neet you can circle that the catalyst decreases the activation energy. Okay, that is not correct, but it will give you credit if the alternate pathway mechanism is not given to you. Alright, now if you see, still this minus this gives me delta H. So I can still say delta H equals E activation forward catalyzed minus E activation reverse catalyzed is delta H. So delta H equals any of these three. So I can equate any of them. E activation forward minus reverse is exactly same as E activation forward catalyzed minus E activation reverse catalyzed. Okay, because all of them are delta H. Delta H is a state function, it's not a path function. These two are different path, but it's a state function. Okay, couple of things you want to go do from the diagram is, if I draw a mirror image of that, okay, அப்படியே இது இப்படி இந்த மாதிரி வரைஞ்சிங்கன்னா மேலேருந்து இப்படி வரைஞ்சிங்கன்னா that will be the potential energy diagram for a endothermic process. இதோட mirror image வரைஞ்சா potential energy diagram for an endothermic catalyzed process. If you take negative catalysts or the inhibitors, what will happen is they raise the alternate pathway mechanism. Okay, இது இன்னும் கொஞ்சம் அதிகமாகும். So E activation forward and reverse both go up, hence they actually lower the rate. Again, catalyst is going to deal with the kinetics of it, not the thermodynamic part of it. Okay, alright. Now what is this point where there is a highest energy? There what you do is you form something called an activated complex. Activated complex are also called transition state. Okay, transition state is represented by the symbol this way. So you draw something and you put it in a square bracket and put transition state, meaning it's unstable. Okay, just these are fundamentals only. It's the highest energy that you are going to have and it's not stable. So once you go to top of mountain, it's not stable. A ball is not going to stay there, it's going to roll to either side. Endha side varundrathu equally possible until the ball starts rolling and reaches this end. இங்கேருந்து நீங்கள் இந்த எண்டு வர வரைக்கும் எது கம்மி எனர்ஜி உங்களுக்கு தெரியாது. மலைக்கு மேலேருந்து ரெண்டு சைடில் பார்க்கும்போது கீழே இருக்கிற மாதிரி தான் இருக்கும். ஸோ இட் ஹாஸ் ஈக்குவல் ப்ராபபிலிட்டி. தென் why does it go forward? Imagine this, let's say there are 100 molecules here, 50 come this way and 50 come this way. Okay, now you put in more energy. What will happen? இந்த 50 இந்த சைடு போகிறதுக்கு எனர்ஜி கம்மியாக தான் தேவை, ஆனால் இந்த 50 இவ்வளோ கெயின் பண்ணணும். ஸோ என்ன ஆகும், இந்த 50ல் இங்கே ஒரு 50 இங்கே ஒரு 50 இருக்குது. ஓகே, let's put it this way. I have a distribution of 50 and 50. Now I put some energy. What will happen is about 30 of this go to the other side. Let's say I have remaining 20. 30 இந்த பக்கம் வரும். இந்த 50லேருந்து ரிவர்ஸில் போகிறது கஷ்டமாக இருக்கும். எதனாலனா ஆக்டிவேஷன் எனர்ஜி அதிகம். ஸோ 50லேருந்து ஒரு 10 தான் போதும், ரிமைனிங் 40. And then 30 of it has come this side. 10 of it has come this side. Now what used to be 50-50 ratio has become 30-70, then 30 il innu konjam indha pogum. So in the long run actually the reaction ends up going to the other side, but this is just the enthalpy perspective of it. There is obviously entropy, and then a combination of that along with temperature will give you free energy, which ultimately decides. But just an example of what you are going to see. Now I am going to use this diagram and do one last thing, an application of potential energy diagram for organic chemistry. Alright, now we saw in organic chemistry, let us say SN1 mechanism. Okay. So now what has happened in SN1 mechanism is, let us say for example you have a carbon leaving group, this goes to carbocation, this with a nucleophile forms this, and that is the slowest step, rate determining step. Okay. Now what this means is, actually this does not go directly here, okay, but if I were to draw a potential energy diagram, this is how it is going to look like. My reactant, and assume that this reaction is exothermic, endothermic na idu inge irukum, does not really matter. Okay. So now this is like this, there is two different places. So this is transition state 1, transition state 2. Anything that is formed in between a reactant and a product is called intermediate. In our case, the carbocation is the intermediate. Okay. This is reactant, this is product. So what is the transition state? Now I am breaking this bond. The bond does not break right away, it breaks little bit. That is my transition state. Similarly, this bond right away does not form, it forms partially. Okay. So those are the transition states. This is how an energy profile will look for an exothermic SN1 reaction, and a carbocation is an intermediate, not a transition state. Transition states are unstable, whereas intermediate, depending on the stability, can be isolated for microseconds, are actually lower than that. Triphenyl methyl carbocation is actually been isolated because it is an intermediate. Intermediate is not stable, okay, but still it is much more stable than the transition state. And when you see the activation energy, see these are the two activation energies. Which one has the higher activation energy? Obviously this one. Hence it is going to have a tough time gaining so much energy to go to that side. Hence it will be the slowest to process, rate determining step. Among a given set of reactions or given set of reactions in a mechanism, the step that has the highest activation energy will be the rate determining step. It will limit the amount a product can be formed in a given amount of time. Okay, so this is SN1. Let us look at SN2. SN2 is straightforward. Let us again assume, let us go for this time, say endo. Okay, so now I have that is what we have. Alright, so let us just put minus and minus. Now how does this look as? Obviously if this is reactant, it is endothermic products, it will not go straight like this, it will go through this. So now I know this is my activation energy. So what is this transition state? Now a bond is cleaved between carbon and leaving group, and a bond is formed between carbon and nucleophile. So the activated complex or the transition state is nothing but carbon, part of the bond is broken with the leaving group and part of the bond is formed with nucleophile. Okay, this is the transition state, and I have actually shown you this in our mechanism. Okay, that is a carbon with 3 different groups attached already, and one bond is broken, one bond is formed partially, so sp2 hybridized. Okay, this is the potential energy diagram for a carbocation mechanism and a SN2 mechanism. Now when you look at it, once I form a carbocation, okay, I can have multiple options. Let us say for example, there is another reaction, something like this. This has higher activation energy, it is a side reaction, carbocation form another side reaction. What if you heat? I am going to get temperature putting, I can cross this activation energy. Okay, that will be a elimination reaction. Elimination, I told you, it always competes with your substitution reaction. Okay, elimination is favored by higher temperature. ஸோ நான் டெம்பரேச்சர் அதிகமாக போடும்போது ஆக்டிவேஷன் எனர்ஜி எனக்கு ஈஸியாக இருக்கும். ரெண்டாவது இந்த ஸ்டேஜில் நான் பாண்ட் ஃபார்ம் பண்ணுறேன், கார்பன் நியூக்ளியோஃபைல் பாண்ட். எனர்ஜி போட்டிங்கன்னா பாண்ட் ஃபார்மிங் இஸ் எக்ஸோதெர்மிக். நான் எனர்ஜி போடுறேன் அப்படின்னா பாண்ட் ஈஸியாக ஃபார்ம் ஆகாது. So I can undergo elimination reaction depending on the product, whether it is more stable or less stable than reactants. It will be exo or endo. But this will give you an concrete idea of what happens in terms of carbocation dynamics. Okay, it always competes with elimination, and this is obviously SN1 na idu enna varukna E1 elimination. E2 is altogether different, it doesn't relate to here. Okay, this is the basis of energy profile for a thermodynamic process. It could be either exo or endo. I will strongly stress that you guys draw your own diagram and draw the endothermic along with it as a mirror image, and make sure that you are getting drawing this in multiple colors, so it's just easier for you to revise. Okay, all right, thank you guys.